Okay, so today we are going to start on section 6.3. We are going to do volumes by cylindrical shells. Now, in our last lecture, I was showing you those computer animations of this process, as well as with discs and washers. So we're going to finish working through volumes by cylindrical shells, and then we're going to review using washers and shells, so with the handout. But anyway, let's start here. Volumes with cylindrical shells. Oh, I need one more thing here. 1 second. There we go. Okay, sorry about that. So when you take a partition right here that's vertical and you're rotating it about a vertical axis, okay, notice this partition is parallel to that axis of rotation there. And, let's see. So when we do this, you're going to create, when you rotate around here, just like here, you create what we call a shell. Okay, so taking this partition, rotating about this axis, we get what we call a shell. It's hard to see, but here's the visualization here. Now, when you create a shell with a rotation like this, there are two radii you have to think about. Well, the shell has a radius and it has a height. Well, right here, this is the height of the shell, which is basically the height of the partition. So we're going to call this right here H. Oops. Now the shell also has a radius, and the radius runs from the axis of rotation to the partition. So if I go over here, you'll see this is actually R, the radius of the shell, and this will be your height of your shell. Okay, so we'll call that R up here. All right, so we have that picture there. Now, the other thing to realize here is the partition, since you're partitioning the x-axis, which is normally horizontal, this little distance from here to here is delta x. Okay, delta x. So the thing we can think about is, okay, if this is a thickness delta x, then actually there's a radius here that goes to the outer edge of delta x and a radius that goes to the inner edge of delta x. So to be more precise, as we develop our equation for the volume of a shell, let's go ahead and specify that, okay, we have a larger R slightly, and let's call that R1. Now that goes to the outer edge of the partition, and then you have a smaller R that goes to the inner edge. Let's call that R2. So in this shell that I've drawn over here, when you take the axis of rotation to the outer edge, we're going to call that R1. And then when you take the distance from the axis of rotation to the inner edge of delta x here, we will call that R2. Now, one thing to keep in mind, when delta x goes to 0, the smaller you make delta x, the closer R1 is getting to R2. So when you take the limit as delta x goes to 0, you're going to realize that R1 will converge to the value of R2. Okay. So all we're trying to do is to develop a formula for the volume of a shell. Now a shell has we can think of it simply as an outer cylinder subtract an inner cylinder, right? So if you look from the top here, what would it look like? Okay, so I'm going to draw this picture here. If you look from the top, you'd have the outer, and then you would have the inner, and the inner would be slightly smaller. So let me go ahead and do that. So there would be your smaller there. So see, this is where the volume is coming from, this edge here. This edge right here is the top right here, okay? And what's this distance across here? Can anybody tell me?
Delta
R1.
X.
Yeah, that's delta x, correct? And see, the larger r that I was talking about, which we called R1, runs to that outer edge, right? That's R1, and over here would be R2, okay? And you can see here that delta x then would equal R1 minus R2, okay? So, oops, I'm gonna move these pictures out of the way now. So we have this over here, and then we'll put this circle over here for you. And we'll put this right here. Okay, so now let's talk about the volume of this shell then, based on what we just wrote down. So the volume of the shell then, okay, would equal the volume of the outer cylinder subtract the volume of the inner cylinder. Okay, remember the outer cylinder has that radius R1 and the inner cylinder has the radius R2. So now when we do this, okay, so the volume of a cylinder is pi r squared h. So the volume of our outer cylinder then would be pi r1 squared h, okay, and our inner cylinder would be pi r2 squared h. And so if we take out the greatest common factor, that would be pi h, right? And then we're left with r1 squared minus r2 squared. Now we can obviously factor the difference of two squares. So what we get here is pi h, we get r1 plus r2, and then r1 minus r2. Okay, now remember, as I mentioned earlier, what was r1 minus r2?
Delta X.
That's right, that's delta x. So now we can write our formula down as pi h r1 plus r2, okay, delta x, okay? So this is our basic formula for the volume of one arbitrary shell, okay? Just this arbitrary shell that's being created from taking an arbitrary partition this is its height, and because it's vertical, we're partitioning the horizontal axis, and that's why it's delta x. Okay, so now that we have this here, we can say, all right, let's see if I can do this now. As delta x approaches 0, R1 is approximately equal to R2. Oops. Well, we should say this way. R1 converges to R2, meaning they're basically equal. Okay. So what this says, since R1 converges to R2 as delta x approaches 0, we can say R1 is basically equal to R2, which we'll just call R, okay, because they're converging to each other. So with that said, therefore, the volume of one arbitrary shell, okay, the volume of one arbitrary shell is equal to pi h, right? And then you have R1 plus R2 delta x, that was our formula there. But what can we say about R1 and R2? Oops. That when delta x goes to 0, R1 and R2 basically become equal. So it's going to become 2R. Because what we're saying here, R1 and R2 become equal. Therefore, R1 plus R2, since they're both R, it becomes 2R. So that simplifies our formula down to this, that the volume of an arbitrary shell then is equal to pi times h times 2R delta x, which finally gives us this formula. It's 2 pi r, correct? Now, if you think about it, what does 2 pi r represent?
Circumference.
Circumference. So when you look at the shell, yes, it's basically this circumference right here, 2 pi r, right? But there's a little thickness, and that little thickness is delta x. So see, the volume of the shell, we can think of it as the circumference of the top of the shell, which is this. The shell has a height, which is h, so let's put that down there. And then what's the thickness to give it its volume? It's delta x. Okay, so right there is the volume for one arbitrary shell. Let me use a different color for that. Let's use this green one. So the volume of one arbitrary shell then is 2 pi r h delta x. And that's the key here, because once we find one of them, we know how to sum things up using the integral. Okay, so in this case, we're going to now put this to work with this function here. Okay, any questions on this part? So here's your general formula for the volume of a shell. Okay, so let's put this to work with a function, which is this part here. Okay, so here's a partition that's vertical, and we're going to partition the x-axis, but what we're going to do is put it below a function f of x, right? So f of x is right here in green. Okay, so basically what you're looking at, I can draw an axis here, make it less convoluted here so you can see it. And then you have a function doing this, right? You have a function going like this, and I'll fix that up a little bit. There's f of x. We do that. And then you had your y-axis here. Now I'll put it about right here. There we go. Okay, and this was your function f of x, right? And so if you take this arbitrary partition now and place it down here, let's extend it a little bit. Make it a little bigger here. Come on. There we go. Oh, I good enough. So there's my partition now. Now, when you think about it, see, when you make the shell, if we're going to rotate this one about this axis here, right, we're going to create a shell. Now, the two things we're looking for in terms of our formula is R and H. So this is the axis of rotation. So the radius of this arbitrary shell runs the distance from the axis of rotation to the shell. Because remember, this shell is going to be rotated around this axis like this to make this shell here that you're seeing up here in this picture. Okay. So we've got our radius. Now the last thing we need is our height, which is this distance here. This is h. And if you realize here, up here at this top point is an arbitrary x comma y value. So it should be clear to you that if this is an xy, remember this distance here is that y value. So in this problem, h is actually equal to y. And we know y is equal to your function. The distance x is from the y-axis to the partition, right? So in here, you can see R will equal X. Okay, any questions on that? Like if this was an ordered pair 2, 3, the radius would be 2 and the height would be 3. But it's arbitrary, so we say XY. Okay, so if we look at this picture up here, notice I have my arbitrary partition drawn right here, right? And as we mentioned here, up here is an arbitrary point right here. And that's at the point X, Y. We'll just call it X, Y. But remember, Y is f of X. So notice the radius of this arbitrary shell is X, and this is your height here. And so in this case, your height would equal the Y value, correct? H would equal Y, which is equal to f of X, okay, for that arbitrary shell. And don't forget, what's the thickness of your shell? The thickness of the shell, because it's vertical, is delta X. See, if your partition was laying horizontally, you'd have delta Y's. Because it's vertical, it's delta X, okay? And so now with that, we can say, all right, let's see here. We can say, all right, then the volume of our arbitrary shell comes from our basic formula, which we derived. It's 2 pi r h delta x. But in this problem, it's 2 pi. And then what's our r value in this problem? What's r equal to in this problem?
X.
X. Very good. And then what's our height here?
Y.
It's y,
Which is also f of x.
which is also f of x, right? So I'll put f of x in there. And then we have delta x there. There we go. So basically you can see our formula then would be 2 pi x times f of x delta x. Oops. Delta x, right? And that right there would be the volume of our arbitrary shell. So the volume of our arbitrary shell would be 2 pi x f of x, where you have to remember x is the radius, right? The radius of the shell, and f of x is the height. And once you've got one of them, then you just integrate from wherever you're trying to find the area. Like this one might say, find the volume of the shape of the, by rotating the area under f of x about the y-axis from 0 to 2. Then you integrate from 0 to 2, you'd plug in x, and whatever f of x is, if this was like x cubed plus 1, that would be x cubed plus 1 dx, and you're ready to go, okay? All right. So now what we're going to do is take a look at another one here, okay, where in this case, we are rotating here a bounded area. Now it's a little bit convoluted. I'll do the best I can. So here is f of x up here, and here's g of x. So what you have here is a bounded area between these two functions. But notice, you're asked to rotate the area bounded between a and b, not from 0 to b, from this arbitrary value a to b. So this shape that's generated is going to have a hole in the middle, right? So that's a little harder one to see there. But the thing is, what we're going to do, just as before, we're going to take our arbitrary partition here, right here. And because we're creating shells, we're going to rotate this around that y-axis, right? But they only go up to here, all the way up to here, from A over to B, okay? So in here, in the middle here, you're going to have this void here. There's like a cylinder going through the middle of this shape here, right? And with all of these problems, you simply just have to remember, I need to find the volume of an arbitrary shell. So with that partition that's drawn here, see, there's my arbitrary shell right there as I throw it in there. And see, that's that arbitrary shell that we're trying to find the volume of. Okay, you take that, you take that partition right here and rotate it around the y-axis is what it's saying, and you get the volume of this arbitrary shell right there. Okay. All right, so I want to get that over there. Oh, that belonged over there, that's why. Okay, so the area that we're working with, the bounded area, remember, is only this region right here that exists. Here's f of x, which is this part up here, and here's g of x, which is right here. So let's write that down so we know that's there. So this is f of x up on top, and on the bottom is my g of x, right? From there. Now, with our arbitrary partition that's drawn right in here, correct? We have a height, and the axis of rotation is the y-axis, so that's r. Now, if we look at an arbitrary point for this arbitrary partition on f of x, this ordered pair up here on the top is x, comma y, but y is equal to f of x, our larger function on this area. If we go to the ordered pair down here, which is on the function g of x, it has the exact same x value as this one, right? They have the exact same x value, but the y value, yes, it's a negative y value because it's coming off of g of x, because that's g of x. Okay, so we can see here that h then, this height from here to here, would be this y value, subtract this y value, therefore it's simply f of x minus g of x. The axis of rotation is the y-axis. So the distance from the y-axis to that partition is just these x values, which are exactly the same. That's why the radius is x. Okay. So make sure we understand, okay, we know that h then, I'm going to write it down here. H is equal to f of x minus g of x, and we know r is equal to x. So once we have that, we just go back to our standard formula for the volume of a shell. The volume of a shell is equal to, remember that circumference of the top, 2 pi r times the height, and a little thickness, delta x. So in this problem then, the volume of the shell is 2 pi. We have an r value and we have an h value. Well, our r value, we already know that r is equal to x, right? But what about our heights? Our heights now is the difference between the larger y value and the smaller y value. So in this case, our height then would be our larger function on this interval is f of x. Subtract our smaller function we know to be g of x. And therefore, there's our height there. So remember, let's do it this way. That's my r, that's my radius, and over here is my height. Okay, and then don't forget we have delta x at the end. Okay, and so from here then, okay, any questions on this? All right, so now what we do, so now we can sum up the shells. Okay, so now we can sum up the shells. So how do we do that? We have an integral, and this is basically your formula. So the volume then is equal to the integral from a to b, oops, but that 2 pi is a constant, so I can bring it out in front. So this is the formula you're going to see in your book. It's going to say, okay, let's sum up these shells. So 2 pi is a constant, we bring it out in the front. Then we're going to integrate from this region a to b. okay? So A to B is this piece here. We'll put that right there. And then it'll say X, right? So X is basically your R value in this case. It's not always going to be X though, right? And then it's f of X minus g of X dx. And this right here is your basic formula for the volume using cylindrical shells. Okay. So the only difference that this one has from the previous is your height was defined as an area bounded between two curves, f of X and g of X. Where if we go back to this one here, see your height was bounded between f of X and the x-axis, which basically meant that your lower function is y equals 0, or in other words, g of X was equal to 0. That's why your height was only equal to f of X. So don't get confused. This height is f of X because it's just the y value. But this height is the difference between f of X and g of X, those two different y values. Okay, there you go. Any questions on that? Okay, let's move on. Example 1, we're going to rotate the area bounded between two curves. And in this case, our two curves are y equal x squared and f of X equals x. So you do always want to draw a picture. So in this case, this is an easy one. Right here, I've drawn f of X equals x. Okay, and we should know automatically that the intersection between x and x squared is going to be 0 and 1. Okay, although if you needed to do that, you'd remember to find points of intersections, right? We can write that out real quick here. Intersection. You set the two functions equal to x squared equals x. So x squared minus x equals 0. So you get x times x minus 1 equals 0. And you get the two intersecting points, x equals 0 and x equals 1. Right? And that makes sense. That's the two intersecting points there. But you have to know g of X equals x squared is below x. And that makes sense because if you put like 1/4, f of 1/4 is 1/4. But g of 1/4 is 1/16. That's how I know it's below. Okay. So I drew the two graphs here, and this is the region we're rotating. So that's what's shaded there. Now, here's an arbitrary partition that I've drawn. Okay. Now, since we're rotating about the y-axis using cylindrical shells, now here's an important thing. If this is your axis of rotation, to create shells, your partition has to be vertical. So in the shell method, your partitions are always parallel to the axis of rotation. So that's something you might want to make note of. So whenever you're doing shell method, the partitions must be parallel to the axis of rotation. So when I rotate the shell around the axis, right, I'm getting that arbitrary shell there. Okay. Now, we know that the volume of an arbitrary shell, so the volume of an arbitrary shell is 2 pi r h delta x.
Professor?
Yes.
How do we know that the x is there and like giving us the thickness of our shell?
You mean delta x?
Yeah.
Delta x is the thickness of the shell, because if you're partitioning the x-axis, remember when you partition an x-axis, right, you're creating delta x's. When you're making partitions like this,
right,
each of these right here are delta x's. because this is the x-axis.
Right, but, I guess, to further my question is, given the point that you have right now, how do we know that that is like where the cylindrical,
Okay,
is,
so
that
I'm just
gives it the
picking,
height?
I'm just picking an arbitrary value of x, and I'm
Okay,
placing it in between 0 and 1. So if I
okay,
place it here, just to keep track of everything, I'm drawing my partition to line up with x. That's all I'm doing there.
okay, understood. Got it,
Okay.
got it, got it. Sorry.
That's fine. So with this case here, I know this is a formula for the volume of the shell. Remember, the two things I need are the radius and the height, right? So here's my formula for the volume of the shell. And in this case, my radius here will simply equal the distance from the axis of rotation to this arbitrary point. Now, this lower point has an x value of x, but its y value is g of x, because it's the lower function. This point up here that lies on the function f of x has the same x value as g of x, but its y value is f of x. So the distance from here to my arbitrary partition, remember, this is x equals 0, and this is my arbitrary value of x. And I had mentioned, if you want to find the distance from the axis of rotation to the location of that partition, this horizontal distance, it's the larger x value, subtract the smaller x value. And since the smaller x value is 0, r is x minus 0, so r is simply equal to x. Now the height, a little bit different. The height is the larger y value, subtract the smaller y value. But the larger y value is coming from f of x, right? So my larger y value is f of x, subtract, what's my smaller y value, which is down here, the lower function is g of x. So that would be g of x right there. Okay. So with that said, then the volume of our arbitrary shell, right, which is this shell right here, is going to be 2 pi, and what's my radius? That's just x, right? And then my height for that shell is going to be f of x minus g of x, right? But what's f of x equal to?
X.
F of x is equal to x, and what's g of x?
X squared.
X squared, right? So my height then is x minus x squared. Okay, and people often get confused, but you have to focus on, these are y values, correct? But this is off y equal x, and this is off y equal x squared. This is a larger y value from this function f of x. This is a smaller y value from this function g of x. And then our thickness there is delta x. Okay, and that's it. So there's the volume of one arbitrary shell. Now, what we do now is, now we sum up our shells on the interval 0 to 1. And that's it. And this will give us our total volume of this odd looking shape here, right? Remember, it's going to have this like triangular space in the middle of it, and it's just rotated this way. And so here it comes. Here's the volume of our shape. 2 pi is constant. We integrate from 0 to 1. Okay. And what do we have left? We have x times x minus x squared dx. And that right there is the integral that's going to calculate the volume of this shape. And when you break it down, right, if you deconstruct it backwards, remember, it's 2 pi, that was your radius, which was just x. Your height was the larger y value minus the smaller y value. Your larger y value came from f of x. Your smaller y value came from g of x. And then dx to represent your delta x. So there you go. Okay. All right, any questions on that one? Doing shells. All right. So let's look at something that, you know, out of the homework set. Like, it depends on what version you have for the number, but we're just calling it an example. So here's the actual problem. It says, rotate the bounded region about the x-axis. Okay. So we have x, y equals 1, x equals 0, y equals 1, and y equals 3. So what you want to do is draw everything separately. Now, I pre-drew everything, but I'm going to draw it and then I don't have to erase it because I'll run out of room. So when you get a problem, here's what your sketch should look like. I mean, you're going to have an x-axis here, right? So we'll call this our x-axis, and this is our y-axis here, right? That's my y-axis there. And I have this function x right here, x times y equals 1. Well, what I'm going to do is say, okay, I know what this graph is. This is just the graph of y equals 1 over x, right? That's this graph here, correct? Or you can think of it this way. Might be easier to think of it as y over x, but it's also x equals 1 over y. But remember, the graph of 1 over x, we should know what that looks like. It's like I drew it in purple here. That's, some people call this the butterfly. It looks like this and like this, right? So this is the graph of y equal 1 over x, but it's the same as the graph of, I'm messing this up here, sorry. It's the same as x equals 1 over y, but that's that graph there. Then we have two lines. We have x equals 0. Well, x equals 0, okay. X equals 0 is the what? That's simply the y-axis, correct? That's this axis here. Okay, so this is this line here is x equals 0. This is x equals 0, which is this line right on top of here. I'll draw it right there. Okay, then we also have the two other lines, y equal 3 and y equal 1. Well, those are just those horizontal lines, right? So if I draw it, here's right here, this is the line y equal 3, and then I have the line y equal 1 down here, y equal 1. So that's kind of your little sketch there. And then when you look at this, where is the bounded region? Well, don't forget, your bounded region is between x equals 0, right, which is here, y equal 1 over x, y equal 1, and y equal 3. So it's right in here. So it should be this region all up in here, right in here. Close enough. There it is. That's basically it right there. Obviously not that shaded out there, so we'll get that out. Well, that's not good. Okay. So let's get that right out there. There we go. So that's your region there. Okay. Now the thing is, okay, where are you rotating this about? It says they want you to rotate this region around the line y equal x. I mean, sorry, the x-axis, which is y equals 0. So you're rotating around this line here, the x-axis. So now here's the thing. To do this in the most efficient manner, rotate this area here. We don't want to use washers. We can, but if we use washers, we'd have to do two separate integrals. So watch what happens. I'll draw an arbitrary partition here. I'll draw an arbitrary partition here like this, right? There's my arbitrary partition. And the thing is, this arbitrary partition is bounded between y equal 3 and y equal 1, that's fine. But when it moves over here, when I move over here, I have to take into account now, it's not bounded between those two lines. It's now bounded between this graph y equal 1 over x and the line y equal 1. So you'd actually have to do two separate integrals, and you have to split it up at this intersection point. So to make this more efficient, to do this in one integral, we say, oh, let me move this out of the way and let me rotate it horizontally if I can. Oh, come on, you're not gonna let me do it. There we go. So I'm gonna rotate it horizontally now. And I see now that when I do this, and I put them up here, let me spread that out a little bit, come on. Work with me, there we go. So now when I put my partition this way, see, it's bounded between the same two functions. It's always bounded by this larger value and this smaller value there. Well, what happened to my partition there? Right there. So let me do that again. If I put it right here, it's bounded between this x value and this x value. Okay, and you're going to rotate this around the x-axis. So when I rotate this around the x-axis, I'm making these shells. And so let me go up here so you can see a little bit clearer here. When you rotate it, when I rotate this around the x-axis, I get this shell that you're seeing right here. Okay. Now, any questions on that? Okay, so that's what we're creating, that particular shell. All right. Okay, so now we should understand this picture that I've pre-drawn up here. Okay. So remember, this was our little sketch down here. All right, so now we have to move this, or actually get rid of this. Now, and then we're going to look at our other picture there. Okay, so now here's a cleaner representation of this picture I've drawn. So here's our bounded area. Remember, this is y equal 3, y equal 1, so this is 3 and this is 1. I'm rotating around this x-axis. Now, remember what I said in the last example. If you're creating shells, your partitions have to be parallel to the axis of rotation. Since my x-axis is horizontal, my partition has to be horizontal. Therefore, you're not partitioning the x-axis, you're partitioning the y-axis. That's why we have delta y here. Okay. So now, I drew an arbitrary partition. Here is my arbitrary shell. Okay. Now we know, first thing I'm going to write down is the volume of one arbitrary shell is equal to 2 pi r h. And this time we don't have delta x, we have delta y. That's the only difference. We have delta y's, so everything's got to be in terms of y. Okay. So now we look at these two arbitrary points. This point right here, right? If I take a point right here, its x value is 0, and the y value is that arbitrary y value. Again, I'm just picking an arbitrary y value. I'm calling that y. That lies between 1 and 3, y equal 1 and 3. And if this is y, then x is 0. This value has the same y value, but you realize, okay, what's its x value? See, this is that little transition here. Remember, this is always x, comma, y. But we need everything in terms of y because we're dealing with delta y's since we're partitioning the y-axis. So if this is x, comma, y, we leave the y alone, but this is x. But this x is coming from this function, which is same as y equal 1 over x, but we're calling it x equal 1 over y because this is now a function of y. So see, this x value here is 1 over y, and there it is. Okay. Any questions on that piece? All right. Let's kind of bring this one home. So what we have now is we have 2 pi. Now, what's my R value here? See, R, remember, we got to think vertically now. The shell is being created this way. Here's the axis of rotation. So the radius of this arbitrary shell will be the distance from the axis of rotation to my arbitrary shell. And how do you find distances? Remember, between 2 places, you take the larger, subtract the smaller. Well, what's the larger y value? It's so easy, it's confusing. The larger is just y. That's my arbitrary y value. What's the smaller one in this case, though?
0.
Yeah, it's y equals 0. So my radius then is just y subtract 0. So it just becomes y. So it's just y. That's my r here. Okay, so there's my r value. It's y minus 0, which is y. Now over here, we're going to put in our h's. Okay, now h is this distance, right? It's this larger x value subtract the smaller x value. Well, what's the larger x value? See, it's not x, it's what? It's x equal
1 over y.
1 over y, because it's coming from this function. So my larger x value is 1 over y. What's my smaller x value?
0.
0, that's it. So my larger x value is 1 over y, subtract the smaller one, which is 0. There it is. And then don't forget, we don't have delta x's, we have delta y here. There you go. So now my volume of my arbitrary shell is 2 pi y times 1 over y, right? 1 over y dy. And this one works out pretty nicely because we just get 2 pi dy. That's it for this particular example. So remember, this is always the tricky part here. We want the volume of one arbitrary shell, and we get it down to this. That's always the hard part, finding out what is R and what's H, and there it is. Once you have that, you've gotten through the most problem. That was what you're trying to learn in this calculus class, how to visualize and set this up. And now we use what we learned in Math 3A, an integral, to sum all these up. So now our volume then of our shape, or our solid that's being generated by this, is 2 pi. And where are we summing up our partitions? Remember, we're summing up our partitions along the y-axis in this shaded region. They're y values. So we're summing up our partitions from y equal 1 up to y equal 3, all the way like this. So our integral goes from 1 to 3, y equal 1, y equal 3. And then we just have what? dy, right? Because that's what there's no y values in there. They reduced out. So this is our integral here. And it's so easy, it's confusing. So what do we get here?
dy or delta y?
Well,
off
I'm
top
sorry.
you say
Yeah.
delta y.
No,
and
yeah, I
then
messed up there. Yeah, you're right. That's confusing there. What did I do wrong? This should have been what? These were delta y's, not dy's yet. Sorry. Thank you. This should be delta y and this should be delta y, okay? They don't become dy's until you let the limit go to what? Infinity, remember? In the Riemann sum? In the Riemann sum, your delta y turns into what? dy. Okay, that was my bad. Okay, remember, arbitrary shell, you have delta y's. But then when you sum them up, remember, you're taking the limit as n goes to infinity summation I equal 1 to n of this function, right? Delta y, and then delta y turns to dy, and so on. All right. So now we can go ahead and finish this integral. What's the integral of dy? Okay. See, you got to realize that this thing here, oops, what happened there? That this thing here is actually the integral of 1 dy, right? That helps. What's the integral of 1 dy?
Y.
y.
Yes, it's y, right? So let me put that back. So what's the integral of 1 dy? It's y. So you end up with just y times y evaluated from 1 to 3. So we get 2 pi 3 minus 1, which is obviously 2. And so your final answer for this volume is 4 pi. So this is the volume, 4 pi cubic units, of taking this shaded region and rotating around the x-axis to make that odd-looking shape, right? Okay. Any questions on that one there? All right. Yeah, you know, what would the shape look like? We can kind of sketch a quick graph of it. So it's going to have an inner cylinder in it, right? Let's see. I'm just going to draw a quick sketch to see it. So we have this inner cylinder here like this, right? And then you have that's the inner cylinder. And then it goes something like, it's hard to see it, right? Let's see. And it comes down something like this, right? To here, and looks like it's flat here, right? Something like this. So that's kind of what it looks like. It's hard to kind of visualize what that thing looks like, but remember, it's all round like this, right? Something like that. It's always hard to visualize those things, right? And then obviously this would come down like this, right? And all in here, all this place is solid around this inner cylinder. So it's some shape that looks something like that, okay? All right.
I actually had a question.
Okay.
Say that y actually, okay, hold on. The horizontal lines y equals 1 and y equals 3.
Uh-huh.
Say that was y equals -1 and y equals -3.
Well,
Would
then-
the A
yeah.
and the B just flip? That's the only change.
Yeah. If you're,
Okay.
oh no, but yeah, but see, then you got to pay attention to, yeah, if the graph still went like this, but then you'd be looking over here now.
Mm-hmm.
Right. And so yeah, it would probably be the same answer there. It's just that, yeah, you'd be integrating from where to where though? From -3 to +1, -3 to -1.
-1.
Yeah. -3 to -1, right?
Right.
Yeah.
So you would just flip kind of the,
Yeah. Yeah. it
yeah,
would
the
be-
A and B and with the sign.
Yeah, but the X, the H, that would be a little tricky here because your H would be different. Your H would not be X. Your H would have to be -X. If you
Okay.
did something like that. And your R would still be, your R would have to be with a partition down here, would be 0 minus Y. So it'd be -Y. You gotta be careful
Gotcha.
with that one.
Okay.
But yeah, it would basically be the same. Any
Okay,
other
dokie.
questions? All right, where we at? Here, it's about time for a break, huh? All right, so let me stop this. We're gonna take a break. Hold on a second.